A very good morning, all of you. Welcome to the lecture number 40. In this lecture, we are going to cover gated latches and flip-flops. So before going to start today's topic, we'll recap the previous class. In the last lecture, we have seen what is meant by basic memory element. We have seen two latches. SR latch based on NOR gates and SR latch based on NAND gates. So these latches going to store 1-bit memory, either 0 or 1. But there are two problems associated with these latches. You are going to have two problems here. The first problem is there is no control input. So since there is no control input, output will change rapidly with input. Even due to fluctuations in supply voltage also. So since there is no control input, the moment if any change took place at the input side, the same change will be affected at the output side. So it is not a desirable property for the digital system. So we need a system which is stable with respect to noise, with respect to fluctuation in the supply voltage. So we need to have a control input for those circuits. If you want to understand a simplest way, let's take a mechanical switch. Let's take a mechanical switch. When you close and open, so during opening or closing, your switch will go on and off several times. Due to non-uniform surfaces. So as a result, your output will change, like in a small period will change multiple times. This kind of behavior we don't want in our digital system. So we need to have a control signal or control input so that we can control the output. Whenever we want to enable the output, we will enable it. Otherwise, it will be in the same state. This is the first problem. So this first problem we are going to overcome by using a extra control input. The solution for this problem is we are going to use one extra control input. So those circuits are called gated latches. Those circuits are gated latches or latches with enable input. We'll see in a moment. This is the first problem and this is the respective solution, and we'll see a detail how we are going to add the control input. Now we'll try to see the second problem. Second problem, if you look at here, we are having invalid states, 1 for NOR latch and 0 for NAND latch. So these are the invalid input combinations. So we cannot avoid this input combination in the latches, but we are going to modify this circuit. The latch circuit we are going to modify so that we don't encounter invalid input combinations. So these are the two problems and there are solutions. Now we are going to see how we are going to add the control input, how we are going to avoid the invalid input combinations. Now we'll start with the control input. So now onwards I'm going to do all the analysis with only NAND gates throughout all the lectures. So any latch I am referring that is nothing but a NAND latch. So we'll take the as usual NAND latch. Your Q and Q bar, your S and your R. For the timing I'm considering this is S star, you can say R star. Now I'm going to add one more NAND gate here and one more NAND gate here. Now I'm going to make this as S and this as R, and second input I'm going to connect with a common line. This I'm going to make it as enable input. To understand this logic circuit, you need to understand the operation of your NAND gate. If one input is 0, it doesn't have to care about the second input. It automatically going to produce the 1 here. If you look at your circuit, this is nothing but your SR NAND latch. This is nothing but your SR NAND latch. For SR NAND latch, if you take your input combinations and your Q and Qn plus 1, if you take S0 and R1, it is going to set the output to 1. Irrespective of the previous, it is going to set to the output 1. If it is 1 0, it is going to reset the output to 0. If it is 1 1, same state. 0 0 is invalid state. Now if the enable is 0, if enable is 0, you are going to get S star as 1 and R star as 1. When S star R star as 1, if you look at your SR NAND truth table, so it is nothing but a memory state, or it's a memory state. At the same time, if S and R changes, when enable is 0, if S and R are changed, it's not going to affect your output. Output is not affected because your enable is 0. This always going to produce output 1 here and output 1 here. When output is 1 here, this NAND latch going to produce the same output as your previous output, that will be in the memory state. So that means your enable input will allow these inputs to apply to this NAND latch or not to apply to this NAND latch. If you look at here, let us assume this is, let's say, some input here. So depending on this value, I'm going to transfer my input to the output side. If it is 0, it is not going to transfer your input to the output side. If it is 1, it is going to transfer your output. Now let us analyze this circuit by using different inputs of S and R. When S is 0, R is 1 and enable is 1. Enable is 1, S is 0, R is 1. Since enable is 1, if you look at the NAND gate action, when one input is 1, other input is an arbitrary name, it is going to produce the A bar. Similarly, in this case, enable is 1, that means going to produce the complement of the 0, that means becomes 1 here. this 1 becomes 0 here. Now you have applied 1 and 0 to the NAND latch. As you know, when you apply 1 and 0 to the NAND latch, it is going to reset your output to 0. That means when S equals 0, R equals 1, you are going to reset your output to 0. When S equals 0 and R equals to 1. Now we'll see the second case. Second case we'll keep. Now let's start with S equals to 1, R equals 0 and enable also 1. So enable is 1, S equals to 1, R equals 0. When S equals to 1, this 1 becomes 0 here, this 0 becomes 1 here. Now you applied S equals 0 and R equals 1 for the NAND latch. So in this case you are going to set your output to 1. That means you are going to set your output Q to the 1. So that means S equals to 1, R equals 0 with enable 1 equals 0 is set state. It is going to set your output to 1. I will take the next condition. Now let's take S equals 0, R equals 0 and enable equals to 1. When S is 0, R is 0, enable is 1. This 0 becomes 1 here. This 0 becomes 1 here. Now you are applying 1 comma 1 to the SR NAND latch. As you know, 1 input for the SR NAND latch is the memory state. So that means you are going to be in the same state as your previous state. That is a memory state. That means S equals 0, R equals 0 is a memory state for the gated NAND latch. Now we'll see the last condition. Now we'll consider S equals to 1, R equals to 1 and enable equals to 1. When enable is 1, S equals to 1 and R equals to 1, this 1 becomes 0 here and this 1 becomes 0 here. As you know, 0 0 input for the SR NAND latch is invalid. So this is a invalid combination or invalid input combination. Now we'll see the last case. Now we don't take S equals S is arbitrary and R also arbitrary. Now we are going to keep enable as 0. S we don't care and R also we don't care. When enable is 0, this 0 becomes 1 here and this 0 also becomes 1 here. When you apply 1 1 to the NAND latch, it is going to be in the same state. That means you are going to get Qn plus 1 as Qn. That is a memory state. Even if you change your S to 1 or 0 or R to 1 or 0, your output is not going to affect. That means you are actually enabled your latch to store a particular information. When the enable is low, it is going to store that particular information as long as your enable is low. The enable goes to high. Depending on the present input combination, it is going to store either 0 or 1. So this is all about your SR NAND latch with enable. I am going to summarize in one place. This is SR latch with enable, or we can call it as a gated SR latch. Now if you summarize, you are going to have a black diagram here. This is your S and this is your R and this is your enable and Q and Q bar. This is SR latch with enable. Now let's make the truth table. S R Qn and Qn plus 1 and your comment. When S is 0, R is 1. Whether your Qn is 0 or 1, your output going to be in the 0 state. This we call it as a reset state. When S is 1, R is 0. Whether the previous output is 0 or 1, you are going to set your output to 1. This is a set state. When both the inputs are 0, 0, whether the previous output is 0 or 1, you are going to be in the same state. Whatever the previous output you are going to have, the same output will be displayed here. When you are having both 1, 1, you don't have to care about the previous output because it is an invalid input combination. Yes. For all these 4 combinations, you are going to have enable as 1. Your enable is 1, enable is 1, enable is 1, enable is 1. Now if you make enable is 0, it doesn't matter what value of S, what value of R, what value of your previous output 1 or 0, it's going to be in the same state as your previous state. So there is nothing but a memory state, or your output is not affected by the change in the input. That's what is meant by control input. Your enable is 0. Even if you change S value or R value, your output will remain in the same state. So this all your SR latch with the enabler. SR latch with enable. Now we are able to overcome the problem of output changing as whenever there is a small change in the input, by simply enabling your SR latch or disabling your SR latch with the enable input. Now we will try to simulate the gated SR latch using read software in a moment. Now let us simulate the gated SR latch with enable. If you look at here, when the enable is 1, if you make S equals to 1, you are going to set your output. You can see clearly your Q output is 1. If you make both 0, 0, it will be memory state. If you look at it, whatever the previous output is in the same state. If I make my reset equals to 1, it is going to reset your output to 0. If I make both 0 again, it will be in the memory state as your previous state. If I make set equals to 1 once again, it is going to set your output to 1. If I make it 0, it's going to be in the memory state as long as enable is 1. If I make my enable 0, now whatever you do at the set and reset place, it's not going to affect your output. That means it will be in the memory state. Whatever the previous memory, whatever the previous output was there, it will be in the same state, irrespective whether S is 1 or 0 or your R is 1 or 0, as long as your enable is 0. As a result, we are able to have a control input for the setting your output to 1 state or 0 state. This is with the a normal enable. Same thing can be done with a clock. Now we have solved the first problem by adding an extra enable input with a extra NAND gates, and we are able to enable or disable our latch for responding input changes or not responding to the input changes. Now we'll see the second problem faced by latches, where we have a invalid input combinations. like if you take a gated SR latch, your 1 input is not a valid input. Now we are going to overcome this problem by modifying a gated SR latch. What we are going to do is we are going to use data latch or D latch or transparent latch. We call all these names as same. So let's take the gated SR latch first. This is your gated SR latch. Now what I'm going to do a small modification here. What I'm going to make one NOT gate here, and this NOT gate will be connected to your R input. Now you have only one input. Only one input. That one input you call it as a D input. Instead of S, we are going to call as a data input or D input. If you look at here, whenever your D is 1, your S is 1, R is 0. Whenever D is 0, your S is 0, R is 1. Now there is no possibility that S and R either may be both zeros or S and R may be both ones. Now if you look at here, we have clearly avoided this invalid combination as well as memory also, but memory operation can be utilized by using enable. When enable is 0, this actually memory operation. The same memory operation can be utilized by making when enable is 0, irrespective of your data, irrespective of your D input, you are going to get one here and one here. When both are 1 1 for the NAND latch, is going to be a memory state. When enable is 0, you are going to get the memory application. So by simply connecting with one NOT gate to our input, we are able to avoid invalid input combination. Now we'll try to analyze this circuit. It is straight away. If you look at here, when data is 0, when D is 0, when D is 0, S is 0 and R is 1. As you know, when S is 0, R is 1, it is going to be reset your output. Similarly, when D equals 1, your S becomes 1 and R becomes 0. In this case, is going to set your output. So you are only two states. One is set when D is 0, your Q1 plus 1 will be reset, and D equals 1, your Q1 plus 1 will be set, provided enable is 1 for both the cases. When enable is 0, you don't have to care about your D value. It is going to be in the same state. Your Q1 plus 1 will be in the Qn state. That is nothing but a previous state. So this is all about your D latch. We will try to summarize in one place with a simple tabular column. So your D latch you are going to have a black diagram. This is your D input and your enable input, and you are going to have Q and Q bar. Since there is only one input, you have only two possibilities. D, it can be 0 or it can be 1, and enable. So first we will make enable 1 and enable 0 for the same combinations. Now we'll take the Qn plus 1. when D is 0 and enable is 1, you are going to reset your output to 0. When D is 1 and enable is 1, you are going to set your output to 1. When enable is 0, you don't have to actually care about your D input. You are going to be in the previous state. Your Qn plus 1 will be a Qn. Similarly, in this case also your Qn plus 1 will be Qn. This is your D latch truth table. So it directly, so if you look at here, whatever the D value you are giving, the same value is stored at the output side. That's why it is called transparent latch. Okay, now with this D latch we are able to overcome invalid input combinations, and with the gated latch we are able to overcome the control input problem. Now we are going to see another kind of problem faced by your gated latches. Now let us see the problems faced by a gated latch. Now we'll see problem faced by gated SR or D latches. If you take a simple block diagram of your SR latch or D latch, this will be S and R, Q and Q bar, and you are going to have one enable input E. Similarly, you are going to have D input and your enable input, and you are going to have Q and Q bar. This is your SR latch and this is your D latch. Now in most of the times we are going to give enable input with a clock. Here also same thing, most of them we are going to give enable input as clock. So as you know, your digital clock is nothing but a kind of square wave with 50% on and off cycle or 50% duty cycle. This will be your 0 and this will be 1. If you look at here, your SR latch will respond only when enable goes to high state. Similarly, your D latch also respond to your inputs only when your clock goes to the high state. If you look at here, your clock will be in high state for a certain amount of time. Let's say 10 seconds. For example, your clock cycle is 10 seconds at high state. Within 10 seconds, if input changes due to noise or power supply issues, your output also going to change. Please listen carefully. In case of gated latches, we are going to use enable input with a clock. Your clock will have a time period of certain time it will be in high state, certain time it will be off state. So whenever it is in a high state, that in that particular duration, if at all if the input changes by due to a system noise or power supply noise, the same thing will be affected by the output side. That means your circuit still not stable, still is not controlled one. So to avoid this problem, what we are going to do is we are going to use the edge triggered. We are going to use the edge triggered latches. Those edge triggered latches are called flip-flops. Please remember, this is the definition of your flip-flop. So the edge triggered latches are called flip-flops. Now if you want to differentiate clearly what is meant by latch and flip-flop, If you want to differentiate the latch and flip-flop, your latches are level triggered. That means your circuit will respond at these places as long as your clock is high. In that entire region, that clock region, your circuit will respond. That's why it's called level triggered. Whereas in flip-flop, which is nothing but edge triggered, in edge trigger, your circuit will respond only whenever clock made the transitions. Whenever clock goes from 0 to 1, similarly 0 to 1, your circuit will respond, or your circuit will be enabled only whenever your clock goes from 0 to 1, 0 to 0. This is called positive going transition or positive edge triggered. Similarly, the circuit can respond negative triggered or negative edge triggered. That means 1 to 0, 1 to 0 and 1 to 0. This is called NGT, negative triggered or negative edge triggered, sometimes called as a rising edge. This is called falling edge. Now the circuit will respond only whenever the clock made the transition from 0 to 1 or 1 to 0. Such circuits all are called flip-flops. Please remember this definition. Any circuit which responds to the clock level, like whenever clock is high for longer time, those circuits are called latches. So in our memory applications, we use only flip-flop because we are going to use flip-flops for the memory applications, practical memory application, because your output is not affected by your noise or system fluctuation, because your circuit will be activated only for a fraction of a second. That we will see how we are going to produce the fraction of a second enable pulse to the flip-flop. Now we'll see edge triggered circuits or flip-flops. What we are going to do is, so these are the level triggered, what we are going to do, I am going to reduce this positive cycle, I am going to reduce the clock to a very small spikes. Okay, this is a level and this is edge triggered signal. Now we are going to produce this signal. This signal will be applied to the latches. That latch will respond only whenever the short pulse applied to the circuit. Now we will see how we are going to produce the short pulse. Whenever clock going from 0 to 1 or 1 to 0, we are going to produce this sharp pulse whenever clock make the transition 0 to 1 or 1 to 0. We are going to see the circuit in a moment, how we are going to produce that. Let's take positive edge triggered. Now we are going to make a simple circuit. This is my clock. I am going to keep these two inputs to a AND gate. Now this is your clock and this is your clock bar. Now if you write the output waveform, let's take the clock. This is your clock. The same clock is applied at B side and clock bar is applied at A side. So clock bar will come little delay because your NOT gate takes some propagation delay. As a result, your NOT gate output starts somewhere here. This is my clock and this is my clock bar. So there is a small delay here because your NOT gate takes some propagation delay to transfer or to invert your signal to the other side. Now if you analyze the circuit, now this is your B input and this is your A input. Now these two are given to a AND gate. Now AND gate output you are supposed to see. If you look at here, at this small portion of space, your A equals to 1 and B equals to 1. As a result, till this place you are going to produce a 0. At this place is going to produce a small spike. Then it will be 0 0. If you look at here also this is 0 and this is 1. So again it will be 0. So it's going to produce a small spike. If you repeat this process, you are going to get small spikes. These small spikes going to enable your circuit. That circuit is nothing but your flip-flop. This is for positive edge triggering. Now if you want to look for the negative edge triggering, this circuit is for positive edge triggering. Now we are going to look for the negative edge triggering. I will see the negative edge triggered circuit. We are going to use the same clock. We are going to use one more bubble here. This is my clock. This is my clock. So this will be clock bar. Clock, and there is one more bubble here. So if you draw the circuit, let's take this your clock. This is your A and this is B. So this is the A input now. So if you look at, there are two bubbles here. So this is a clock, and if you look at, this becomes clock bar. So it will start little earlier than expected. This will be your B. So this is your clock. This is your clock at this place. This clock is applied here and get 2 times inverted. It becomes clock with a delay. And the same clock again inverted here by 1 time. So it is having a small delay here. This having more delay and this having a lesser delay. Now if you look at here, at this place this is 0 0 0. All this place it is 0 0 0. And this is 1 and this is 0 0. Okay. But if you look at this small region of space, where you are going to have A equals to 1 and B equals to 1. So as a result you are going to get a small spike here. Okay, similarly if you have many number of cycles, you are going to have small spikes. These spikes will be applied to your gated latches to act as a flip-flop. So now we are going to I'm going to show you simulated output of your both positive edge triggered circuit and negative edge triggered circuit in a moment. So this is your positive edge triggered circuit. So whenever clock take transition from 0 to 1, it is going to produce a small positive spike. I will try to simulate this and we'll try to see these are your waveforms. I'll simulate it. We'll make the time scale to 1 second. Now you can see the clock signal. This is a clock signal and this is your output signal. Now we are going to see how it is going to produce your output. You can clearly see here. You can clearly see here when our clock goes from 0 to 1, it is producing a small spike. Similarly, 0 to 1, it is producing a small spike. Similarly here, let's zoom it and let's see. Look at very clearly, there is a small spike here when our clock is moving from 0 to 1. Same here, 0 to 1, it is producing spike. If you repeat it for many cycles, you are going to see a series of spikes at the output port side. Now you can clearly see for each clock transition from 0 to 1, it is producing a small spike. This spike will be applied to your SR latch and that SR latch will act as a flip-flop. This is for the positive edge triggering. That means when our clock goes from 0 to 1 only, it is going to produce a positive spike. I will try to see the negative edge triggering in a moment. This is a negative edge triggered circuit. Whatever we discussed just now, we will try to see. Let's make the scale bar 2 seconds since I kept my clock frequency in seconds. Now you can see this is your clock and this is your output. That output we are going to see in a moment. Let's run and we'll try to see. Now you can see the spikes are generating at the output port. But if you will observe carefully, your spikes are observing it when our clock is taking from 1 to 0. 1 to 0 here and 1 to 0 here and 1 to 0 here and 1 to 0 here. So that means this is a negative edge triggered because your positive spikes are generating when our clock is taking transition from logic 1 to logic 0. So this is how you are going to apply these spikes to your latch circuit to work it as a flip-flop. That we'll see in a moment. Now we are clear about the positive edge trigger and negative edge trigger. Now we are going to study the SR flip-flop and D flip-flop. Your SR flip-flop is nothing but SR latch or gated SR latch, which will be triggered by either positive going transition or negative going transition. Similarly, your D flip-flop also nothing but D latch or gated D latch, which will be triggered by either positive going transition or negative going transition. In a simple bar diagram, we can show your SR flip-flop something like this. This is your S input and this is your R input, and you are going to have a arrow symbol here. Arrow symbol is nothing but a clock, and if there is no bubble, it's a positive edge triggered, and this is your Q and this is your Q bar. This is your SR flip-flop now because it is a edge triggered. Similarly, when you take negative edge triggered, what you are going to add an extra bubble here. This will be Q and this will be a Q bar. In this case, this is a negative edge triggered. So this negative or positive edge triggered will be useful when you analyze the waveforms. So this circuit will respond only whenever clock goes from 0 to 1, and this circuit will respond whenever clock goes from 1 to 0. That means whenever clock goes from 0 to 1, it's going to produce a small spike. In this case, whenever clock goes from high to low, it is going to produce a small positive spike. So now this is called SR flip-flop. Suppose if you remove the clock, if you replace edge triggering with a normal clock, then we call flip-flops as latches. Please remember this is the difference, because your latch respond to level triggering. That means this entire region your latch will respond. So that's why it's called latches whenever you use a normal clock or any enable input. But whereas in case of flip-flop, it will respond only whenever clock make a transition. That means clock is nothing but a circuit. The circuit is called edge detector circuit. Similarly, this clock also nothing but a extra circuit. This also edge detector circuit. So usually we don't show in the diagram. We'll just say that it is a positive going clock transition and negative going clock transition, or positive edge trigger or negative edge triggered. Similarly, in case of D flip-flop also, you are going to have your D input. This is your D input and this is your clock. So since there is no bubble, this is a positive edge triggered, and this is your Q and this is your Q bar. And if you want to use negative edge clock triggered, then in this case you are going to write D, then your clock with a bubble, and your Q and Q bar. This is your D flip-flop. Now we will try to see the truth table of SR flip-flop as well as D flip-flop in a moment. Let's take SR flip-flop. In case of SR flip-flop, now we are going to have a truth table with clock S, then R, then Qn plus 1. Qn plus 1 is nothing but the next state. When the clock is making transition, please remember you have to analyze circuit only whenever clock make a transition. So this arrow mark is nothing but your clock is going from 0 to 1. When clock is going from 0 to 1, it's going to produce a small positive spike. So based on your input, is going to produce the output. When both are 0 0, it will be in the memory state, or whatever the previous, it will be in the same state. Similarly, when again one more clock is activated, in this case suppose if you make SR input 0 1, it will be a reset state. Your Qn plus 1 will be 0, or you can call it a reset state. Similarly, when S is 1, R is 0, you are going to set your output to 1. This is set state. Similarly, when the clock is activated and your both the inputs are 1 1, it is a invalid state or invalid input. Now when clock is not activated, so that means when the clock is 0. So if you look at this clock waveform, this will be something like this. If you look at here, more than 90% your clock will be in 0 state. So when clock is 0, please remember this very important. When clock is 0, you doesn't have to care about your SR inputs. It is going to produce the same state as your previous state, or we call it as a memory state. So this is your SR flip-flop truth table. Please remember. Suppose if you want to analyze the same circuit for negative edge trigger, only difference is you need to change this arrow marks to downside. Suppose this is for positive edge triggered Suppose if you want to produce a negative edge trigger, what you are doing, you are supposed to make your arrow marks down, and this will be as usual zeros, and rest will be same, and you have to add a bubble here for showing a negative edge triggered flip-flop. Now we'll try to see the D flip-flop truth table. As you said, you are going to have one input for D flip-flop and one clock. This clock is now positive edge triggered since there is no bubble, and this here Q and this here Q bar. Will make the truth table your clock D and Qn plus 1. When clock is making the transition, if D is 0, you are going to get output as 0. When the clock is making the transition, when D is 1, you are going to get the output 1. This is reset, and this is set. When clock is 0, irrespective of your D input, your Qn plus will be in the previous state, or you call it as a memory state. So this all for the D flip-flop. In the next class we will see what are the problems associated with the SR flip-flop and D flip-flop, and how to overcome those problems by using another flip-flop in the next lecture. Thank you all.